So our next topic is quadrupole moment. Nuclear quadrupole moment. So normally the shape of the nucleus is spherical in standard models, but because of some uneven charge distributions and uneven number of charged particles, means if there are odd number of protons, there will be some uneven distribution of charges. Okay, so because of that, or even if the charges are even in number, even if the protons are even in number, because of their angular momentum distribution, the shape of this nucleus may not be spherical always. So the charge contribution is given by this is the charge distribution in the nucleus. Here R is x square plus y square plus z square. So if the charge distribution along x, y, z, all the three directions are equal, if it is uniformly distributed, we will get 0. So if x is y is z, I mean radius of the sphere along x direction and y direction are equal, then q is 0. Otherwise, so if 3z square is greater than r square, means what? X and y are less than z. So the shape of the material becomes like this. You will have a little more extension along z direction, and both x and y contributions will be lower compared to z. So then 3z square will be greater than r square. So this type of shape is called prolate. And another possibility, 3z square is less than r square. So then xy plane extensions are more compared to z. So this is called oblate shape. Okay, so these things arise because of the uneven distribution of charges, even if they are even in number. So if a even distribution of charges, net dipole moment will be 0. Dipole moment means what? What is dipole moment? Or x, whatever. Charge multiplied by separation between the charges of opposite nature. So here the charge distribution is quadruple in nature. That means positive negative charges are distributed into 4 pieces. Okay, so we have to look for the contribution or interaction between these charges. So the charge distribution equation is this. Okay. for this kind of charge distribution, we may have two different shapes of the nucleus. So if it is not perfectly spherically symmetric, then we'll have contributions for quadrupole moment. So even if the dipole moment becomes 0, means separation between positive and negative ions is 0. So where from do we get that negative is the question. We're talking about nucleus. Within the nucleus.
పాజిటివ్ ఛార్జ్ ఒక్కోసారి దీని ఛార్జ్ దీంట్లో ఉన్నది ఛార్జ్ లాస్ అయ్యి దానికి ఇవ్వడం అలా జరిగినప్పుడు 2 ప్రోటాన్స్ మధ్య నెగిటివ్ పాజిటివ్ రెండు కూడా డెవలప్ అయ్యే అవకాశం ఉంది.
Okay, that we'll see in the next session. Anyway, right, so that's a thing to be discussed. Okay, mark it. So next one is magnetic moment. So this is a nice contribution from Bohr, that whenever a charge revolves in circular orbits, it produces magnetic field. Moving charge produces magnetic field, and the direction of the magnetic field is given by right hand thumb rule. So if thumb gives you the amperes rule, right? If thumb gives you the direction of current, curl of fingers gives you the direction of magnetic field, right? So if the charged particle moves in anti-clockwise direction, what is the direction of magnetic field? It will be expelling out of the loop. Always it will be expelling out of the loop. So this is the direction of magnetic field. So in total there will be an upward magnetic field orientation when the charged particle is moving in circles. So if the particle is moving in anti-clockwise direction, you will see a north pole along the direction, perpendicular to that plane. Okay, so the magnetic moment is given by IA, current times area. Current is what? Charge per unit time. So here I am considering a positive charge, so it is positive charge of electron. Current is charge per unit time. Area is what? Displacement by velocity. Is it? Okay. It is pi r square. Pi r square is the area of that circular part. So now I have to look for charge. Charge is okay, and about time. What shall I write? I should write displacement by velocity. Time. What is distance by velocity? So you cannot talk about displacement in circular motion. So distance by velocity gives you the time of travel. Okay, the charge particle covers an area of pi r square or covers a distance of 2 pi r with velocity v. So what do you get? Pi cancel. EVR by 2. So this is the magnetic moment produced by that charge. Okay. So if we make some modifications, angular momentum by 2e. So this is, in terms of quantum numbers, it is square root of L into L plus 1 h bar. So this is Eh bar by 2m L into L plus 1. So that is the magnetic moment produced by unit positive charge. And if you substitute mass of proton, you will get a particular number. So this part is called Bohr magneton. So I can write it as mu is equal to mu b times square root of L into L plus 1. So this mu b is Bohr magneton defined for electron. And for proton and neutron we have different concepts, like mu for proton is Eh bar by 2 times mass of proton, and for neutron it is Eh bar by 2 times mass of neutron. Okay. So they are the So what does this dipole moment deal with? So you have equation for energy related to magnetic field. It is magnetic field strength multiplied by magnetic dipole moment. The same mu. In the same way, electric field multiplied by electric dipole moment gives you the energy. For any physical quantity, for any activity that we do in any field of physics, usually will be linked with energy. When ultimately we have to look for conservation of energy in any physical activity. Right? So when you are dealing with magnets, when you are dealing with electric field, even in thermodynamics, your pressure and volume are conjugate pairs. Right? Once you start varying pressure, the effect will be reflected in volume, and the product of those two gives you energy. The same way, entropy and temperature lead to energy. So ultimately, this gives you an information about how the energy is being consumed or how the energy is being distributed in that activity. Right? So when you are dealing with magnetic field, it produces magnetic dipoles. So when you bring a magnet near to iron piece. Dipoles will be induced, right? So what is the effect of that energy utilized in the form of magnetic field is the result is a dipole moment. The same way, when you are dealing with electric field, the effect of electric field on any system leads to electric dipoles. So the energy utilized in the process of creating dipoles with this field. I mean, this is the equation links that entire activity. So energy is a product of field multiplied by dipole moment. That means the energy in the form of electric field is consumed to generate dipoles. Or energy in the form of magnetic field is utilized to generate magnetic dipoles. So the product of these two will give you the energy consumed or energy utilized, energy required for an activity. So everywhere in physics you will come across some set of physical quantities which will be linked to energy ultimately. I mean, that will be the starting point for the study in that field. So in electricity, this is the starting point. In magnetism, this is the starting point. So in thermodynamics, the product of pressure and volume, whatever thermodynamic potentials, fields and potentials, they are the starting point of thermodynamics. Even in mechanics, you have Hamiltonian, Lagrangian. All these are the starting points of study various systems or various interactions or various conversions of energy. Okay? Right. So rest of the things we'll see in the next session.